The final confidence interval that we're going to look at deals with variance and standard deviation. We've dealt with mean, we dealt with proportions, but how are we going to determine the standard deviation of the sample, where it would fall in relationship to the population? Again, a lot of times we don't know the population items. We don't know the parameters. In this case, we don't know the standard deviation, but we do have it from a sample. This is the formula we're going to use right here. This symbol right here is called chi-squared. And we're going to have a chart similar to the t-distribution in which we'll be able to find that. Degrees of freedom still n minus 1. One thing of note here is that this is written correctly. Even though the left is on the right hand side and vice versa, what ends up happening here is this number is going to be larger than the left number. Well, we need a larger denominator because we want the left hand side of this to be smaller. It'll make sense in a couple seconds. Notice that our chi distribution, our chi curve, which is right here, doesn't look like a normal curve to start. But as my degrees of freedom increase from 2 to 3 to 4 all the way up, as you get close to, let's say, 100, for example, it will start to resemble the normal distribution. It is very skewed right otherwise. So let's look at an example. So in this problem, find a 90% confidence interval for the variance and standard deviation 16, so my n value is 16, and they're giving me the standard deviation of 2.1 months. Well, I went to the table, which hopefully you have with you, and I looked up degrees of freedom 15, because my n value is 16. I want a 90% confidence interval, which basically means if I were to draw my chi-squared, it's going to look something like that. Again, skewed to the right. Well, if I want 90%, that means I'm cutting 5% off this side, and I'm cutting 5% off this side. So I'm going to focus here, and I'm going to focus here. 5% off the left, 5% off the right. So when I go to set this up, I go back to my formula. My formula says take n, subtract 1, take your deviation and square it, which will give me variance, and put that over top of my right hand chi-squared value. Do the same thing for my maximum. 16 minus 1, 2.1 squared. I'm going to use the 7.261. When I evaluate both sides of this, I'm going to end up with 2.65 and 9.11. This is the interval for my variance. My variance is going to fall somewhere between, I'm 90% confident that it's going to be somewhere between 2.65 and 9.1. To turn this just simply into standard deviation, I would take the square root of everything. That will eliminate the square. It's going to be 1.63 to 3.02. So what I can say about my confidence interval, I'm 90% confident that the standard deviation of the population is somewhere between 1.63 months and 3.02 months. Example 2. Very similar setup here, except what I'm looking at is I have an n value of 24. And I'm looking at a 95% confidence interval. As I always suggest, I'm going to draw myself a curve here. Now it's going to start to look like a normal curve only because n's starting to get big. My degrees of freedom, I want 95%, so I'm going to cut off 2.5% on both sides, which will give me this number, and it will give me that number. So I go through, I plug everything in. In this case, they're giving me a variance. That's s squared of 5.29. Since it's already squared, I don't have to square it. It's already variant. So I'm going to use the 5.29. Don't square that number. 38.076, which is this number here. Same setup on top. $11.689, and this is going to give me the interval for my variance. Again, this is variance. Don't square that number. So my variance is going to be somewhere between 3.20 and 10.41. If I take the square root, I'm going to get my standard deviation. So I am 95% confident that the standard deviation of ages of seniors is between 1.79 years and 3.23 years. The reason we do this, if we don't know the population standard deviation, it's going to limit some things that we can do in the future. If I have a range, if I have an interval in which it must fall, now I can determine, is it a relative value? How can I use it? What does it talk about? Things along those lines.